What is AVL tree? This tree has named after its three inventors. Okay, that is Adelson, Felsky, and Landis. So now today we'll discuss about this one, this AVL tree, which is named after its inventors, Adelson, Wilsky, and Landis. So before starting this tree, at first we need to know about the binary search tree. Do we know what is binary search tree? Yes, binary search tree is a tree where the left subtree is greater than the root node, and in right subtree all the nodes are greater than the root node. Suppose some key values are given, that is 3, 2, 5, okay, so these are some values 4, 2, 5, 1, 3. So how we can create the binary search tree? In a way where the left subtree, all the nodes in the left subtree will be less than the root node, and in the right subtree all the nodes will be greater than the root node. So here the first node is 4, so we can add it as a root node. Then the next node is 2, so after comparing it with 4, we can see that 2 is its value is less than the root node. So in which subtree we'll add it? In the left subtree. Now the next node is 5, which is greater than 4. So add it in the right subtree. 5 is the right child of 4. Now the next node is 1. At first compare it with 4. It's less than 4, so go to the left subtree. Here in the left subtree there is a node 2. So again compare 1 with 2. 2 is less than 1, so it will be added as the left child of 2. Now the next node is 3. So where we can insert it? In the right subtree of 2. So this is a binary search tree where all these nodes in the left subtree are less than the root node, and in right subtree 5 is greater than 4. Okay, so when we create this binary search tree, at that time did we calculate the balance factor? Did it calculate the balance factor? It's a new term for us, right? Balance factor. So after creating a binary search tree, we don't know whether it is a balanced tree or not. So what is balanced tree? This is the left subtree of 4, and this is the right subtree. And we know how to calculate the height. How to calculate the height of a node? Just take a leaf node in the longest path, then calculate the total number of edge between the leaf node and the root node. Isn't it? What is the way of calculating the height of a node? Suppose the node is 4. So how we can calculate the height? Just take a leaf node in the longest path. So there are 3 leaf nodes. 1, 3, 5. One is in level 1 and another is in level 2. So this is the longest path. So now if we calculate the number of edges between 4 and 1, how many edges are here? 2 edges. Right? That means for this tree, the height of the root node is 2. Okay, so now in a binary search tree, how we can find out whether that tree is balanced tree or not? So for finding it out, we have to calculate the balance factor. Okay, so what is balance factor? So now take this leaf node 1. This is a leaf node, that means this node doesn't have any left child or right child, and this is same for 3 and 5. They're leaf nodes, so they don't have any left child or right child. So what about this node 2? 2 is a parent node who has two children. One is left child and another is right child. So now can we calculate the height of this root node? For this root node, now if we consider the left subtree as well as the right subtree, find out the height of that node in the left subtree as well as in the right subtree. This is the left subtree for 2, and how many nodes are here? Only 1 node. So there is 1 edge between 2 and 1. So the height of the left subtree of 2 is 1. Now what is the height of this root node in the right subtree? in the right subtree, the height of this root node is 1. Now, how to calculate the balance factor? Balance factor is actually the difference between the height of the left subtree of a node and the height of the right subtree. So for this node 2, the height of left subtree is 1 and the height of right subtree is 1. So the value is 0. Now, find out the balance factor of 4. In left side, in the left subtree, its height is 2. How many nodes are here? How many edges between this leaf node and the root node? 2 edges. So the height of the left subtree of this root node is 2 and the height of the right subtree is 1. So what is the balance factor of the root node? 1. That means for this entire tree, the balance factor is 1. The balance factor of a tree is actually the balance factor of the root node. Okay, so when for this node 2, the balance factor was 0. For this node 1, 3, 5, the balance factors are, what is the balance factor? For these nodes 2, 1, 3, 5, 0. But for the root node, the balance factor is 1. So can we call it a balanced tree? Yes. So we can call it tree balanced tree where the balance factor is -1 or 0 or 1. What does that mean? That means the difference between the left subtree and the right subtree cannot be more than 1. The height of the subtrees cannot differ by more than 1. So if it is a root node, in the left subtree there are how many edges are here?
2.
Between the leaf node and the root node?
There is 2.
2. That means there are 2 levels. And in the right subtree there is only 1 level. So the difference between the height of the left subtree and right subtree is 1, and this value is within this range. So we can call this tree a balanced tree. Okay, so what about this one? Suppose now the root node is 2 and it's 3. Okay, its left child is 1 and its right child is 4, and 4 has another left child, that is 2. So is it a balanced tree? It's a binary search tree. Why? Because this is the root node. Is it a binary search tree?
Yes, ma'am.
Yes, ma'am.
It's not binary search tree because 2. This is the left subtree for the
yes, ma'am,
root node.
Left side.
And in the right subtree, the node value cannot be less than 3. So here we can take 5. Suppose 5 is the right child of 3 and here the value is 4. So now this is a BST or binary search tree. So now can we calculate the balance factor of this tree? The balance factor of a tree is the balance factor of the root node. And how we can calculate it? Balance factor is the difference of the height of the left subtree, that is HL, minus the height of the right subtree, HR. Okay, so here in the right subtree there is only one H, so the height of left subtree is 1, but the height of right subtree is 2. So 1 minus 2 equals to -1. So is it a balanced tree? Yes.
Yes, ma'am.
Because in the left subtree now there is 1 level, but in the right subtree there are 2 levels. So now the height of the subtree, the difference between the height in left subtree and right subtree is 1. Okay, the difference cannot be more than 1. So now we can take another subtree, suppose 10, and the left child is 6, the right child is 17, and 6 and 17 both have 2 child. One is 2, another is 7, and here the left child of 17 is 11 and the right child is 18. So is it a binary search tree?
Yes.
Yes.
No, ma'am.
Why
there
not?
is 11 on the right side.
Is it a binary search tree or not?
No, not binary. Oh, yes, ma'am. Yes, ma'am.
Binary search tree. Okay, because the root node is 10 and all the nodes in the right subtree are greater than 10. Okay, so now it's a binary search tree, but still we don't know whether it's a balanced tree or not. The balance, if the balance factor is -1 or 0 or 1, that means the tree is balanced tree. And how we can find out the balance tree of a of a tree? By calculating the balance factor of the root node. So if it is a root node and we can take a leaf node from the left subtree, then we can take a leaf node from the right subtree. So here the difference or the height of this root node in the left subtree is
2.
2
2 minus
and
2.
the height of the right subtree is 2. So 2 minus 2 equals to 0. It's also a balanced
Sub.
tree.
Yes.
Okay, so now we have to use the concept of balanced tree in AVL tree. Okay, so can you start AVL tree now? First tell me, is it clear to you what is balanced tree or how to calculate the balance factor?
Yes, ma'am.
Okay, so the main concept is the difference between the height of the subtrees cannot be more than 1. Okay, so it's possible that maybe the left subtree has one level more than the right subtree, or the right subtree has one level more than the right subtree, or they have equal numbers of level. Okay, so now the next one is AVL tree. So what is AVL tree? It's one kind of BST. That means if some nodes are given, we have how we can create the AVL tree, just like the binary search tree. That means the left subtree, all the nodes in left subtree will be less than the root node, and the right subtree, all the nodes will be greater than the root node. Okay, but now in AVL tree, after inserting a node in the subtrees, every time we have to calculate the balance factor. We have to check whether the tree is balanced tree or not. Is it clear? Suppose some nodes are given A, B, C. These are some alphabetical values, so they don't have any numbers or values. So how you can decide that this one is the highest than the others? Is it possible to decide which one has the highest value? Yes, it's possible because A is or B is greater than A and C is greater than A and B. Isn't it? How we can arrange all the alphabets in ascending order A, B, C, D, E, F. That means A is less than B and C, right? So if this sequence is given A, B, C, how we can now create the binary search tree? We are trying to create the AVL tree, but at first we have to create the binary search tree with these 3 nodes. So at first insert the first one A. So A is the root node. Now the next node is B. In which subtree will add it?
Right.
B is greater than A in the right subtree. But this is AVL tree. This is not binary search tree. So after inserting a node, calculate the balance factor. A is a leaf node or it's actually a root node, but it doesn't have any children. So its balance factor is 0 minus 0 equals to 0. The height of the left subtree is 0 and the height of the right subtree is 0. So its balance factor is 0. So we can write it here. So now after inserting A is the root node. Why will insert it in the right subtree? Because B is greater than A. After inserting the node, now again calculate the balance factor for all the nodes. B is a leaf node. That means it doesn't have any left child or right child. So its balance factor is 0. But what about the root node?
1.
In the left child, there is no left child for A, but it has a right child. So there is one H. The height of the left subtree is 0, but the height of the right subtree is 1. So 0 minus 1 equals to minus 1. And we know that the range of the value is minus 1, 0, and 1. If the balance factor of any node is minus 1, 0, or 1, that means the tree is balanced tree. So in this tree, all the node balance factor is 0 or minus 1, so this tree is balanced tree. So now after adding the third node, where we'll add it? B is greater than C. That means it should be added in the right subtree. Right? C is greater than A and it's also greater than B. So where we'll add it? In the right subtree. So after adding it, now calculate the balance factor. In AVL tree, first the condition is the AVL tree it needs to be a binary search tree, and then calculate the balance factor. The balance factor cannot be more than its value cannot be 2 or cannot be more than 1. Okay, so the value can be minus 1, 0, or 1. So C is a leaf node. So the difference between the left subtree and right subtree is 0. For B, it doesn't have any left child, but it has a right child. So its balance factor will be 0 minus 1 equals to minus 1. So it's also a valid value, minus 1. What about the root node? In the left tree, there are no child nodes. So 0 minus In the right subtree, there are two nodes. So 0 minus 2 equals to minus 2. The height of the right subtree is 2. So when the value of the root node is minus 2, that means this tree is not a balanced tree. If the tree is not balanced tree, can't call it AVL tree. This is not AVL tree. So now how we can make it a balanced tree? So there are some ways, there are 4 ways for making the unbalanced tree balanced tree. The first one is by using left rotation. Okay, so look at the figure. How we have created the tree after every time we have inserted a new node in the right subtree, isn't it?
Yes, ma'am.
Or when we want to store some data in ascending order, at that time we have to always store the data in the right subtree. So that's why this, suppose the next data is D, why we'll add it in the right subtree of D. When all the data elements are inserted in this way, that tree is called right skewed tree. What is the name of this tree? Right skewed tree.
Skew. Okay.
Okay, so now how we can make it a balanced binary tree? Balanced tree, that means each node should have the balance factor 0, minus 1 or 1. So we don't need to change these two nodes, but this one should be changed. That means we have to change the whole tree. Now we have to find out the infected area. Okay, the balance factor of A is minus 2 and this tree is right skewed tree. So how to make it a balanced tree? By using the left rotation. One option for making it binary search tree or balanced tree is left rotation. Or you can write LL rotation. Okay, so LL rotation, that means some nodes from this side should be pulled down to the left side. This is a left subtree, isn't it? That means we are going to take some node from the right subtree and we will add it in the where? In the left subtree. The first option is for making it a balanced tree, we can use left rotation, that is LL rotation. This is our tree. I'm writing the structure here again, A, B, and C. Left rotation, that means some nodes from this side will be taken to the left subtree. Okay, so the first node is A, that means A should be taken in the left subtree, right? So after removing A from the root node from here, which one will be added in the in this level? B or C? Obviously the immediate one.
Yes, ma'am.
We are using which notation? Left rotation. So take a node from this tree in the left side. So after taking A from this level, now which one will be taken? The middle node. The middle node will be chosen as a root node. So here B is a root node. Now we can add A as the left child of that root node. And C is the right child of B. We don't need to change it. Is it clear how we are making this unbalanced tree is balanced tree? By using left rotation. Left rotation, that means take some nodes from the right side and add it in the left subtree. So which node has taken A? Take the root node and make it the left child of the new root node. And which one is the new root node? The middle one will be selected as the root node. Now is it a balanced tree? We can calculate the balance factor. The height, the difference between the height of left subtree and right subtree is 0 because A is a leaf node. And for C, the balance factor is 0. What about B? The height of the left subtree is 1 and the height of the right subtree is 1. So 1 minus 1 equals to 0. That means this is a balanced tree now. Is it clear? When we are inserting some nodes in an AVL tree or after inserting a node, we have to check whether it's a balanced tree or not. Okay, so when the tree is not balanced tree, we can make it balanced by using left rotation. Left rotation, that means we can take some nodes from the right subtree, then we can add it in the left subtree. Is it clear?
Yes, ma'am.
Okay, now the next option. Suppose now the nodes are given in this order: Z, Y, X. Suppose we want to store the data in descending order, or we can take actually C, B, A. These are 3 nodes. Okay, So at first we will take C. C is the root node. Okay. Now the next node is B. So its value is less than C or greater than C.
Less
Less
than
than
C.
less than C.
Less than, that means it will be added in the left subtree. So B is the left child of C. Then the next node is A. A is less than C, yes, and A is less than B. So we can add it in the left subtree. So when all the nodes are added in the left subtree, that tree is called left skewed tree. What is the name of this tree? Left skewed tree. Okay, but is this a AVL tree? We didn't calculate the balance factor, isn't it? So after taking C, now calculate the balance factor, 0.
It's 2.
Then when we added B, what is the balance factor of B? 0. But the balance factor of C is now difference between left subtree and difference between the height of the right subtree. So 1 minus 0 equals to 1. So it's a balanced tree. But now when we have added another left child, that is A. Now what is the balance factor of A? Its balance factor is 0. What about B? Now B has one left child. So its balance factor will be 1 minus 0 equals to 1. And what is the set of the balance factor? Minus 1, 0, 1. Okay. So now calculate the balance factor of C.
It's 2.
The height of the left subtree is 2 and the height of the right subtree is 0. That means its balance factor is 2, which means that it's not an AVL tree, it's not a balanced tree. So how we can make it balanced tree? Can we use the left rotation here? No, because all the nodes are taken in the left side. All the nodes are taken in the left side. Okay, so for making it a balanced tree now, we can use the second option, that is right rotation. Right rotation or RR rotation. So this means take some nodes from the left side and add it in the right side. That is right rotation. Okay, so always the middle one will be taken for adding in the root node. Okay, so this middle one will become the root node. That means C will be added as the right child of B. So after using this method, after applying this rotation, right rotation, now the new tree will be like this. C will be pulled down here. So C is the right child of which node? Of B. So now B has become the root node. So C is the right child of B, and already A has already been taken as the left child of B. Okay, so after performing this rotation, now again calculate the balance factor. For A, its balance factor is 0. For C, 0. For B, 1 minus 1 equals to 0. Now this tree is a balanced tree. Is it clear?
Yes, ma'am.
So this is a balanced tree, but is it a AVL tree? If we want to create a AVL, you have to make sure that we have satisfied both the condition, that is this tree is a binary search tree as well as all the nodes have the balance factor within this range, minus 1, 0, 1. Okay, so here the balance factor of these nodes are 0. That means this is a binary search tree as well as it's a balanced tree, so we can call it AVL tree. Is it clear?
Yes, ma'am.
Okay, so now maybe the nodes can be given in this order. Suppose A, after that C, and then B. Okay. So at first we can take A as a root node and see is it greater than A or less than A. C is greater than A, so it will be added in the right subtree. But before that, calculate the balance factor. When we added only one node, that is a root node, its balance factor was 0. Okay, but here after adding two nodes, the balance factor of C is 0 because it doesn't have any left or right child. But what about A? It doesn't have any left child, so its height of the left subtree is 0, but the height of the right subtree is 1. So 0 minus 1 equals to minus 1. So it's a balanced tree. Now insert another node B. So where will insert it? C, and current node is C. At first compare B with A. B is greater than A, go to the right subtree. B is less than C, so add it where in the left subtree. So after adding a new node, now again calculate the balance factor. For B, the balance factor is 0. For C, the height of left subtree is 1. The height of right subtree is 0. 1 minus 0 equals to 1. For A, now the height of the left subtree is 0 and for right subtree is 2. So minus 2. So can we call it balanced tree now?
No, ma'am.
No. But is it a left skewed tree? It's not left skewed tree and it's not right skewed tree. We didn't insert these two nodes in the left child or in the right child. The first node was inserted in the right side and this node was inserted in the left side, the left subtree. That means now we have to use both of these rotation, right and left rotation. But which one should be used first? Look at this. Whenever we started any traversal methods, from where we usually start, we always take the, in pre-order or in post-order sequence, you always take the leaf node, isn't it? We always take the leaf node. So here, at first, we will change this sequence. When the nodes are inserted in right and left subtree, and if the tree is not balanced tree, now we have to apply both the left rotation and the right rotation. It depends on the appearance of the nodes, that is in which subtree you have inserted the first node, in the right subtree, and the second one is left subtree. So for changing this one, we need to use the opposite one, that is the right rotation, isn't it? Here we'll use right rotation. For changing this one, we will use left rotation. So which one will be used first? The right one. Okay, so here we will use RL rotation, that is right left rotation. So in this rotation, how to change the sequence of the nodes? I already told you the middle one will become the root node. So how we can change them now? At first, change this one, apply right rotation on this part. So how to apply it? We will not change A first. Okay, so this is A and C is the right subtree, right child of A. And here, which rotation will be applied? Right rotation. That means we will take some nodes from the left subtree and we'll add it in the right subtree. So which node will be taken? C. Obviously C. So C will be added as the right child and this node will be added as the root node. So B will be added as the root node and then C will become the right child of B. After performing right rotation, we got this tree. Okay, now again calculate the balance factor. Actually, we don't need to calculate the balance factor because we know that the balance factor of root node is minus 2 because we didn't perform the left rotation yet. So now look at this. After performing a right rotation, this tree is now a right skewed tree. So in this right skewed tree, we have to apply left rotation. So apply the left rotation. So this B, the middle node, will become the root and this A will become the left child of B. So after performing this left rotation, now the new structure of this tree will be like this. B, its left child is A and its right child is C. Now calculate the balance factor. For A and C, they are leaf nodes, so their balance factors are 0. And for B, the difference in heights are 1 minus 1, so the balance factor is 0. So is it a balanced tree now? Yes, it's a balanced tree. So how many rotations we use? We got 3 cases. The first one is for left skewed tree, use right rotation. For right skewed tree, use left rotation. When the nodes are inserted both in left and right subtree, use right left rotation or left right rotation. Okay. So now the last case. So here, suppose the datas are given. At first C is given and then A, after that B. Okay, so insert the first node C. What is its balance factor? 0. Here its balance factor is 0. Now insert the next node A. So is it less than C? Yes, so add it in the left subtree. Now the next node is B. Compare it with C.
Compare.
B is less than C. Go to the left subtree
Okay.
and compare it with A. B is greater than A, so add it in the right subtree. So now we inserted a node in the left subtree first and the right subtree. Now calculate the balance factor. For B, the balance factor is 0. For A, the balance factor is -1. 0 minus 1 equals to -1. And for C, the balance factor is 0 minus 2 or 2 minus 0. 2 minus 0.
Minus 0.
Now for C, in the height of the left subtree is 2 and the height of right subtree is 0. So 2 minus 0 equals to 0. Sorry, 2, which means that it's not a balanced tree. Okay. So which rotation will be used here? At first we'll change this one, and in which side we added the node? Right side. That means at first use the left rotation. So here we'll apply left right rotation. Left right rotation. So at first this one will be changed. That means some nodes from the right side will be taken to the left side. So B will be added as the root node and A will be added as the left child of B. So after one rotation, that is left rotation, this will be the structure of the tree. So now look at the tree. It's a left skewed tree. All the nodes are taken in the left side. So now apply the right rotation. That means take some nodes from left side to the right side. So B will, the middle one will become the root node and C will be added in the right subtree. Okay, so after applying this rotation left right, now calculate the balance factor. For A, the balance factor is 0. For C, it's 0. And for B, the balance factor is 0. So this is a balanced tree. Okay, so if we want to make a AVL tree, we have to make sure that the tree is binary search tree as well as the tree is balanced tree. And there can be some cases where we'll find, or after adding some nodes, maybe the tree will not be a balanced tree. So how we can make it balanced? By using 4 options: left rotation, right rotation, left right rotation, or right left rotation. Is it clear?
Yes, ma'am.
Okay, so now we can insert some nodes in AVL tree. Okay. So these are some values: 64, 1, 44, 26, 13, 110, 98. So some nodes are given. So how to make a binary search tree? This is a binary search tree. 64 is the root node, then 1 will be the left child, and 44, where will insert it?
Left side.
Right.
No.
Okay.
Yes, so at first compare with 64. 44 is less than 64, so we'll add it in the left subtree. Then compare it with 1. 44 is greater than 1, so 44 will be added in the right subtree of 1. And the next node is 26. It's less than 64. It's greater than 1, so go to the right subtree, but 26 is less than 44. And the next node is 13. Where will insert it? As the left child of 26. 110, it will be added in the right subtree of 64, and 98 will be added here. This is binary search tree. Can we call it an AVL tree? No, because we didn't check the balance factor. So how to add this, how to create the AVL tree? At first, take the first node. So at first, we will insert 64. Okay. So after inserting 64, now the next thing is check the balance factor. What is the balance factor of 64? 0. It doesn't have any right or left subtree, so its balance factor is 0. Now the next step is insert 1. So compare 64 with 1. 1 is less than 64, so it will be added where in the left subtree. After inserting a new node, now again check it whether it is balanced tree or not. We have to calculate balance factor for each node of that tree. So for 1, the balance factor is 0, and for 64, the balance factor is 1 minus 0, that is 1. Because it has one left subtree, but in the right subtree there are no nodes, so its balance factor is 1. So is it an AVL tree? Yes, because it's a balanced tree. The balance factors are minus 1, 0 and 1. Okay. Now insert the next node. Insert 44. At first compare it with 64. 44 is less than 64. So go to the left subtree. In left subtree there is already one node 1. So compare it with 44. 44 is less than 1. Sorry, greater than 1. So add it in the right subtree. Okay. So after adding another node, then you can check. Calculate the balance factor. For 44, the balance factor is 0. For 1, the balance factor is 0 minus 1. The height of the left subtree is 0 and the height of the right subtree is 1. So 0 minus 1 equals to minus 1. For 64, the balance factor will be 2, isn't it? In the left subtree, there are 2 edges. The height of the root node is 2. 2 minus 0 equals to 2. Is it clear why it is 2? Hello?
Yes, ma'am.
Yes, ma'am.
Okay. So is it a balanced tree now?
No, ma'am.
Is it a balanced tree? No. That means use the rotation. However, is it a left skewed tree? No, it's not. Right skewed tree. At first we inserted in the left subtree and in the right subtree. So which rotation will be used? Left, right. LR rotation will be used. So here at first we'll apply the left rotation, isn't it? So at first we'll apply which rotation? Left. So 64 is the root node. It has one left child. And how we can change it now? 44 will become the root node and 1 will be added in the left subtree, isn't it? So now 44 is a root node and 1 is a left child. So it's a left skewed tree now. Apply right sequence, right rotation. That means move that node in the right subtree. So now the new structure will be 44, and now 64 is the right child of 44 and 1 is the left child of 44. Now calculate the balance factor. These are leaf nodes, so their balance factors are 0. And for 44, the balance factor is 1 minus 1 equals to 0. Clear?
Yes, ma'am.
Is it clear?
Yes, ma'am.
Okay. So now insert the next node, that is 26. Insert 26. Okay. So compare it with the root node 44. 26 is less than 44. So where we'll add it? In the left subtree. In the left subtree there is a node 1. Compare it with 26. 26 is greater than 1. So add it in the right subtree. Okay. So now after inserting another node, now calculate the balance factor. For 26 and 64, the balance factor is 0 because they are leaf node. What about 1? 1 doesn't have any left child, but it has a right child. So its balance factor will be 0 minus 1, that is minus 1. Okay. What about 44? In the left subtree, the height of the left subtree is 2 and the height of the right subtree is 1. 2 minus 1 equals to 1. So is it a balanced tree?
Yes, ma'am.
Yes, ma'am.
Yes, it's a balanced tree, so we don't need to apply any rotation here. Now the next, can I remove this part, this one?
Yes, ma'am.
Oh, okay. So now we insert which node? 13. The next one is insert 13. So compare it with the root node 44. 13 is less than 44, so add it in the left subtree. In the left subtree there is already a node 1, so compare it with 13. Is it greater than 13? Sorry, is it greater than 1? Yes. So go to the right side. and 1 already has a right child. So compare it with 13. 13 is less than 26. So 13 will be the left child of 26. Okay, so after inserting 13, now we can calculate balance factor. For 13 and 64, the balance factors are 0. For 26, the balance factor is 1 minus 0 equals to 1. The height of the left subtree is 1 and the height of right subtree is 0. So 1 minus 0 equals to 1. What is the balance factor is 1? What is the balance factor of 1?
1 minus 2.
Sorry?
-2.
Minus 2, because the height of left subtree is 0 and the height of right subtree is 2. 0 minus 2 equals to -2, which means that it's not balanced tree. Now the infected area is this one. This node is the infected node, so we have to change it. Okay, so we have to change this whole area. So which rotation will be applied here? At first we added one node in the right subtree and another node in the left subtree. So we'll apply RL rotation, right left rotation. At first we'll change this one. So how to change this part? 13 is a left child of 26. Now we have to take some nodes from the left subtree, then we can insert it in the right subtree in this way. So which node will be taken in the right subtree? The root node 26. So here I'm writing it here. 1 was the infected node, and now we are changing this 2 node. 13 will become the root node and 26 is the right child of 13. Okay, so after applying this rotation, now this is the right skew tree. So apply which one? Left rotation. Left rotation, that means some nodes will be taken from the right subtree and will be inserted in the left subtree. So 1 will be moved to the left subtree and 13 will become the root node. So 1 is the left child of 13 and 26 is the right child of 13. Okay, so 1 was the left child of 64 and in the right 44. And 64 was the right child of 44. So the balance factor of 1 was -2, and when you got this one after inserting 13. So this is not a balanced tree, so apply this rotation right left, then create a new tree. Okay, so after changing it, now calculate the balance factor. For 1, 26, 64, their balance factors are 0. What about 13?
0.
Its balance factor is 1 minus 1 equals to 0. Okay, then what about 44? It's left subtree. In left subtree, the height is 2. In right subtree, the height is 1. So the height of 44 is, the balance factor is 1. That means this is a balanced tree. Clear? Now the next one is 110. You have to insert 110. Okay, so this is our tree where we'll insert a new node, that is 110. So 44 was the root node and 13 was the left child of 44. Right child is 6. 13 has 2 children, 1 and 26. So now where do we insert 110? Add it in the right subtree. So compare it with 64, it's greater than 64, so it will be the right child of 64. So after of this subtree will be same, 0, 0, 1. What about this 110? Its balance factor is 0. For 64, the balance factor is 0 minus 1 equals to -1. What about 44? The height of the left subtree is 2. The height of the right subtree is 2, so its balance factor is 0. All the balance factors are within this range. That means this tree is balanced tree, right?
Yes, ma'am.
That means we don't need to apply any rotation here. Now insert the next node, that is 98. Okay, so where will insert it? Find out the location of 98.
Left
On the
side of
left, 110.
1.
Left, yes, in the left subtree of 110. So I'm writing it here. So how we can insert 98? This is 44. 13 is the left child, 64 is the right child of 44, and there are two nodes, 126, and the right child of 64 was 110. Now the new node is 98, so it's less than 110, so it will be added as the left child of 110. So after the new insertion, now again calculate the balance factor. For 126 and 98, the balance factor will be 0, right? And what about the node 13? Its left child is height of the left subtree is 1 and height of the right subtree is 1. 1 minus 1 equals to 0. For 110, in the left subtree the height is 1, in the right subtree the height is 0. So the balance factor is 1. For 64, in the left subtree the height is 0, but in the right subtree the height is 2. So 0 minus 2 equals to minus 2. Now this is the infected one. We have to change this one. First we inserted in the right subtree, then the left subtree. So which rotation will be applied? RL rotation. That is left and right rotation. Okay, so at first we will change which one? This one. Here we will apply the right rotation. From this left subtree we will take a node while in the right subtree. So I'm just taking the infected area, that is 64, 110 and 98. So 64 and 110 was the right child of 64. Now how we will change it? 98 will become the node, and we are applying which rotation here? Right rotation. So 100 will be shifted to the right side. So now 98 is a root node and 110 is the right child of 98. So this is the right skewed tree. We will apply left rotation. Left rotation, that means 64 will be moved to the left side and 98 will be the root node. So 98 and 64 is the left child of 98. 110 is the right child of 98. Okay, so now we can add this portion here. So after 98, the new will be 44, 13, and here we have changed this one, isn't it? So now the root node is 98, and it has two children, 64, and another is 110. And for 13, there are two child, one is 1, another is 26. Is it a balanced
Yes, ma'am.
tree? At first we have to calculate the balance factor. 126, 64, 110. All these nodes are leaf nodes, so their balance factors are 0. 13 has one left child, one right child. So the difference is 0. 1 minus 1 equals to 0. For 98, it's also 0.
44.
What about 44?
1 0.
2 minus 2.
Subtree, the height is 2. In right subtree, the height is 2. So the balance factor is 0. That means now this tree is a balanced tree. Is it a binary search tree? Also in the left subtree are less than 44 and all the nodes in the right subtree are greater than 44. This is a binary tree. If the tree is BST and if the tree is balanced tree, that means the created tree is an AVL tree. Is it clear how to create an AVL tree?
Yes, ma'am.
So, any question in AVL tree?
No, ma'am.
No. Okay. So, in today's class, I just showed you how to insert the tree, how to make the tree. So, in the next class, we will delete some nodes from the AVL tree. Okay.
Alright, ma'am.
So if you don't have any question, I can take the attendance. Okay. So please respond.
Yes, ma'am.
One.
Yes, ma'am.